In this video, we're going to introduce 3 new mathematical symbols. So far, we've got the symbols and, or, not, implies, and if and only if. So our 3 new symbols are, first of all, an upside down A, which means for all or for every, a backwards E, which means there exists, and this symbol that's like sort of like a backwards is an element of sign, and this means such that. So a heads up here is that this symbol is not introduced in our book. However, this is a really common mathematical symbol and phrase to use, especially when we're using universal quantifiers. So I wanted to include it, but pay special attention to how it's used in this video because it is not in our text. So the first one we're going to look at is the universal quantifier, and that universal quantifier, again, is that upside down A. This upside down A means for all, or for every, or for any. So to use in a sentence, for example, we could say, for any integer x, 2x is an integer. For any x in the integers, 2 times x is also in the integers. That's a true statement, and that's how we could write that. Then the existential quantifier, there exists a, or there is a. There is an integer such that n is greater than 100. So we could write that as there exists an n in the integers such that n is greater than 100. So here we have that phrase such that, and this phrase such that is written as a backwards is an element of sign. So it means such that or for which, and it's a very common mathematical phrase. So for example, there is an integer n such that n is greater than 100. We could write that sentence as there exists an n in the integers such that n is greater than 100. So let's look at a couple examples. For each of these, I'd like you to read the following statements out loud to yourself, translating that symbolic logic into English. And then I'd also like you to write out these statements fully in English without their mathematical symbols and determine whether each statement is true or false. So take a look at each of those statements below, pause the video, grab a piece of paper, read them out loud to yourself, and write them out in English, and then we'll look at them together in just a moment. Okay, so our first one is for all x in the integers, or for any integer x, there is a y in the rational numbers such that x is equal to 3y. Or if we're writing that out, for any integer x, there is, and we could say a y in the rational numbers, or we could just say a rational number y. There is a rational number y such that x is equal to 3y. So that would be writing this out sort of in English. We do still have the is equal to, which we could write out in words if we wish, but it's not really necessary. Let's see, is this a true statement? Yes, if y is equal to x over 3, then since x is an integer, then x over 3 is a rational number, and so yes, this statement is true. There is some rational number, y, that makes this true, and that number is y equals x over 3. So yes, this is a true statement. Next, for any natural number n, there is a natural number m such that m is less than n. So for any natural number n, there is a natural number m such that m is less than n. We could also read that as for any n in the natural numbers, there is an m in the natural numbers such that m is less than n. Either way is fine. Now, is this a true statement? Let's see. So if, n is 10, then yeah, that's a true statement because we could say like m is 8. Okay, great. But what if n is 1? That's a natural number. Now there is no m in the natural numbers such that m is less than n. So it's false in this one case. That means this entire statement is false. It is not true that for any natural number n, there is a natural number m such that m is less than n, because, here's my example, n is a natural number such that this is not true. So this overall statement is false. All right, next, there is an n in the integers such that n is prime and n is even. So we could say there is an integer n such that n is prime and n is even. Now that is a true statement. That is true because 2 is such a value. 2 is in the integers and it satisfies both of those qualities. If this had been a upside down a instead of an there exists, then that would be a false statement. It's not true for any integer, but it is true for some integer. There exists some integer that makes this statement true. Next, for any x in the real numbers, there is a y in the real numbers such that y squared equals x. So for any is that upside down a. For any x in the real numbers, there is a y in the real numbers such that y squared is equal to x. So is that a true statement? For any x in the real numbers, there is some y in the real numbers such that y squared equals x. Well, let's see. We're starting with for any x in R. So let's say x is equal to, 3. Then y equals square root of 3 is in the real numbers, and y squared equals x. Great. But what if we said, how about for a different real number? Let's say we had x equals -1. Then we'd say, okay, well then following that example, y is the square root of -1, but that's not in the real numbers. Oh no. So there exists no x in the real numbers. All right, there exists no y in the real numbers such that y squared equals -1. That's our definition of an imaginary number. The number I, such that I squared equals -1, is an imaginary number, not in the reals. And so this overall statement is false because it is not true for any x in the real numbers. Okay, let's look at a few more examples. So I'd like you to do the exact same process. Read the following statements out loud to yourself, write them in English without mathematical symbols, and determine whether each statement is true or false. So again, I'm going to give you a moment to think about that, and I'm going to pause, and I'll encourage you to pause the video. Okay, so our first one, for any x in the open interval from 0 to infinity, there is some y in the real numbers such that y squared is equal to x. We could write this, there are definitely different ways we could write this, but one we could say is that for any positive number x, if x is in the open interval from 0 to infinity, that means that x is greater than 0 and less than infinity. It's a positive real number. There is some y in the real numbers. We could also say there is some real number y. There is some y in the real numbers such that y squared is equal to x. So that's how we would write that out loud. or how we would say that out loud and how we would write that. Now, is that a true statement? Yes, we've sort of edited our previous example. Previously, so we saw that if x was less than 0, we ran into an issue. So yes, this is true. If x is greater than 0, then square root of x equals y is an element of the real numbers and has the property that y squared is equal to x. So that's a true statement. Next, there exists a y in the real numbers such that for any x in the positive real numbers, y squared is equal to x. So there exists some real number y such that for any positive number x, y squared is equal to x. Now note, this is very similar to the statement above. It's just that we've reversed the way that we've reversed the order of these two statements. So the order of those two phrases have been reversed. Is it still true? There exists some real number y such that for any positive real number x, y squared is equal to x. So, we've got some y that is fixed. There exists some real number y is fixed, such that for any positive number x, y squared is equal to x. So y squared equals 4 and y squared equals 3. It's true for every positive number x. Well, clearly this is false. There is no single y such that y squared is equal to every positive number. Y squared cannot simultaneously be 4 and also 3. So this statement is false. And so just a note that the order of these phrases matters. So the order of those phrases really makes a difference in determining whether they are true or false. The phrase above with a different ordering was true, but this phrase now, where we've switched the order of those two phrases, is false. Okay, next, we've got for any rational number x, for any x in the rational numbers, there exist integers m and n such that m over n is equal to x. For any x in the rational numbers, for any rational number x, there exist integers m and n such that m over n is equal to x. Is that a true statement? Yes, that's basically the definition of a rational number. So if x is a rational number, it can be written as a fraction of integers where the denominator is non-zero. So yes, this is a true statement. And lastly, there exists some set B such that for any set A, B is a subset of A. There exists a set B such that for any set A, B is a subset of A. Now, is that true? Is there some set B that always meets that requirement? Yes. If B is the empty set or the null set, then we know that the empty set is a subset of A for any set A. So this is a true statement. Now let's go backwards. Let's write the following phrases in symbolic logic. So take a look at those phrases below, pause the video, and write in symbolic logic using those symbols we've been using. We can use there exists, for all, such that, not, and, or, implies, if and only if. We can use any of those symbols. So take a look, try those out, and we'll talk about them in just a moment. The first one, the square of every real number is non-negative. So every, or for any, for all, for any x in the real numbers, x squared, the square of x, is non-negative, is greater than 0. So that's one way that we could write that phrase. Next, there exists a real number whose square root is 7. There exists an x in the reals such that the square root of x is equal to 7. Yes, that is true, and this is true as well. For every real number x, if x is negative, then the absolute value of x is equal to negative x. For any x in the reals, if x is less than 0, then the absolute value of x is equal to negative x. So that is a true statement. So for example, for example does not prove it, but just to see why that is true, if we have x equals -3, then the absolute value of x is +3, which is equal to -3. So that is a true statement. Anytime we have a negative integer, the absolute value of it is the positive version, which is the opposite of negative, the original. So this is true. Now, we could also write this in a different way. We could also write for any x in the real numbers. If then, we could also write as an implies statement. X less than 0 implies absolute value of x is equal to negative x. That's another way we could write that statement. Next, for any prime integer greater than 2, x is odd. For any x in the integers such that x is greater than 2 and x is prime, x is odd. Again, we could also write that as for any x in the integers, x greater than 2, x prime implies x is odd. So that's another way we could write that statement. Again, this is also a true statement. So let's just think about those last two just a little bit, those places where we could use an implies statement. So the first one, we said for any x in the real numbers, x less than 0 implies the absolute value of x is equal to negative x. This could also be written as just x less than 0 implies absolute value of x is equal to negative x. So what I want to highlight here is that an implies statement is assumed to be a for all statement. So in other words, the statement P implies Q, if P of x implies Q of x, is understood to be the statement for all x. P of x implies Q of x. So an implies statement really is a universal statement. So implies really is a universal statement. To enforce that idea a little bit more, if P and Q are statements or open sentences, then if P, then Q is always a statement, and that statement is true if Q is always true when P is true. Or another way to think about that is this statement is true if it's impossible for P to be true when Q is false. And it's false if there's at least one instance where P is true but Q is false. So just with that reminder, I'd like you to take a look at the next couple, those next couple statements, and determine whether they are true or false. So take a look at these, pause, and just think about whether those statements are true or false. So our first one, x greater than or equal to 4, implies that x is greater than or equal to 2. We could also write that for any x greater than or equal to 4, x is greater than or equal to 2. That's another way we could write that. And this is a true statement. If x is greater than or equal to 4, it is also true that it's greater than or equal to 2. Next, A in the power set of B implies that A is a subset of B. We could also write that as for any A in the power set of B, it is the case that A is a subset of B. A is a subset of B. This is true. It's the definition of the power set. The power set of B is the set of A such that A is a subset of B. The power set of A is the collection of subsets of B. And so, yes, if A is the power set of B, is in the power set of B, then A is a subset of B. Next, x is an even integer, implies x plus 1 is odd. So if x is an even integer, x, an element of 2z, implies x plus 1 is odd. We could say that, or we could say for any x in 2z, any x in the even integers, x plus 1 is odd. Yes, this is a true statement. And lastly, x is even implies x is not prime. This is false. So if x is even, then x is not prime. In most cases, that is typically true for most x. Any x greater than 2 that is even is not prime, but x equals 2 is even and is prime.